Good afternoon, class. Today what I'd like to do is to go over the Lewis dot structure. So in this, the Lewis dot structure is a way to visually see the valence electrons in an element. So what I did was I took the first 10 elements right here, hydrogen through neon, and I thought it would be a good way to show you not only some of the differences in the Lewis dot structure, but also the very typical way of showing the Lewis dot structure for especially valence electrons, for valence elements with valence electrons. So here we go. So we have our definition over here, and we have some examples. So hydrogen, you write out first thing you do, you don't have to write this name right here, but what you do have to do is write out the chemical symbol. So that would be H for hydrogen, and again He for helium, lithium is Li, beryllium is Be, etc. What you're going to write is what you're going to now do is put a dot right above or right alongside the chemical symbol so that you can then see how many valence electrons there are. And there is a specific order in which you go to help make sure that you're not confusing different bonds or different pairs of electrons, because if there is a pair of electrons that needs to be together, it needs to be together, and if you follow these rules in this Lewis dot structure, you will always be correct when it comes to where the pairs of electrons are, because we have to remember we have to follow Hund's rule, and that Hund's rule actually comes by and comes through very strongly, especially when we start getting into chemical bonds. So here we go. We're starting with the first period, or the first row, which is hydrogen and helium. What you notice is that hydrogen starts with one black dot. Helium has two black dots that are right next to each other. Well, wait a minute. I don't see that pattern repeating over here with lithium, because that's the next row, row 2 or period 2. Lithium has one dot on top, but beryllium has one dot and then one dot on the side. So why does helium get two dots right up here? The reason for that is because helium is a noble gas. So if helium, being a noble gas, has a completely full set of valence electrons, it will hold on to those valence electrons, they will pair together, and therefore will not work with anything else. So that's why helium looks like a special case over here, but I thought it would be worth pointing out because you generally won't see this specific case, in other rows of the periodic table. So we move on with the more typical examples, which is lithium has one, beryllium has two, and so if you're noticing, what we're doing is we're writing one at the top, one on the side. The next in the pattern would be one below, which is exactly what you see in boron. We have 1, 2, 3. Carbon is 1, 2, 3, 4, and it has 4 valence electrons, so far so good, we're on track. Nitrogen, this is where Hund's rule starts coming in, because right now what I've got is 4 valence electrons, none of them are paired up right now. They're all able to form chemical bonds later on. They're available for that. With nitrogen, however, you start to see something different, because now you've got 1 dot, 2 dot, 3 dot, 4 dot, and then the 5th dot has to pair with the nitrogen, the first electron that we had. So imagine these were the spin up electrons. So spin up, spin up, spin up, spin up. This one is now going to be the first spin down electron. Also, I'll make a point of this later, given these Lewis dot structures, it'll actually be easier for you to see why certain elements, especially if you look in the columns of the periodic table, will give you different types of bonds. For example, you might notice that nitrogen tends to get triple bonds, carbon tends to get single bonds with everything, oxygen tends to have double bonds, and fluorine will tend to have single bonds, although those fluorine bonds tend to be more ionic than anything else. However, we'll see, but that'll come later. So I will get to those in a little bit, maybe in the chemical bonds video. But this one for now is just the Lewis dot structure. So as you can see, 1, 2, 3, 4, 5. So we go around the circle first, and then we start pairing up the electrons. Like you see in oxygen, 1, 2, 3, 4, 5, 6. valence electrons, so we start plugging them in around the circle. And when we get around the circle twice, we have now a fully noble gas right over here. Fluorine, on the other hand, as you can see, has 3 pairs of electrons and 1 not paired electron. This is where all the chemical bonds and all the chemical reactions start to occur with fluorine, because you have to understand, pairs of electrons don't like to separate unless there's a really high energy that's delivered to it. Pairs of electrons stay paired together. And of course, that's why also as the other conclusion that we can get is that neon, because it has 4 pairs of electrons, or as we said from the octet rule, a complete set of valence electrons, it doesn't bond with anything. It takes a whole lot of energy and a whole lot of various schemes and conditions where neon will bond with anything, because it takes so much energy to get rid of any of these electrons. Because they're all paired together, they're very comfortable with each other. So this is an example of the Lewis dot structure on how and how they're supposed to look. What I'll go over in a future video is when we get to chemical bonds, I'm actually going to put some of these elements together and show you exactly how they tend to bond. So that is all for this video. Good luck on your studies. May the force be with you.